Sorry. Okay.
Hello, everybody, and welcome again to the European Non-Associative Algebra seminar. It's a pleasure to introduce the speaker of today, Ilya Chevyrev from the University of Edinburgh. The title of his talk is Algebras in Stochastic PDEs. Please.
Okay, thank you very much for the introduction and also for the invitation to be here. I admit I'm not a common speaker actually at algebra seminars because my own field is in probability and perhaps analysis, but maybe sort of stochastic analysis to be precise. The topic that I want to speak about today is somehow related to non-associative algebras because it's a particular instance where ideas from non-associative algebras, and in particular Prelie algebras, played a very important role in my research. So, in particular, they played a very important role in the problem of renormalisation of stochastic PDEs, which is a problem that I'll describe, and then I'll try to explain how Prelie algebras entered this problem. So this is based on joint work with Yvain Bruned, who I actually believe spoke at this series of the seminar series some time ago, Ajay Chandra and Martin Heirer. And this work is not the most recent. It was up on the archive back in 2017. It was published in 2021, I think. But this is somehow a piece of work that's still somehow very relevant in my own research. So I felt that it was kind of still maybe perhaps appropriate to speak about it here. And so I also wrote some lecture notes about this more recently in 2022, in case you're interested. Okay, so let me begin by explaining what the problem that we're trying to study is all about. So we're going to consider random or stochastic partial differential equations. So these are, which I'll abbreviate to SPDEs. So the kind of equations that I'm going to be looking at are going to be always initial value problems. So there's some initial value here that I haven't written. So there's going to be some U0 here that would maybe is a sort of a continuous function on the torus or something like this, maybe, or some distribution on the torus. I'm going to evolve this. I'm going to try to solve for this PDE, which is going to always be a heat equation. So the leading component, the linear part, is always going to be a heat equation, followed by some nonlinearities. The nonlinearities are multiplied by stochastic objects. These are these xi's that are going to be sufficiently nice noises. So think of them, maybe they could actually not be noises. They could be constants. So for example, there could just be f of u here without anything else. In this case, this is a deterministic PDE. But in typical applications that we have in mind, and I'll present some examples of this on the next slide, these will be random distributions, something like space-time white noise. And again, because I want to emphasize the algebraic component of the problem, or rather its solution in this talk, I'm not going to go into so much detail as to what the nature of these noises is, but I'll explain their important properties later. Okay, so these f's are going to be just smooth functions, and they're going to be smooth functions depending on the solution and possibly its derivatives. So f of u, it's the gradient of u, and maybe high order derivatives. Okay, so let's look at a couple of examples. So a very famous example that's been studied in quite a lot of detail, and was one of the motivations for a lot of the work that's been done in the field here, is the so-called dynamical 5-4 model. So this, so here the 4 is really this. So this 3 is really the 4 minus 1. So because it comes from a quantum field theory that has a power 4, this is its gradient, so you get a cube. And this 3, it's the same 3 as this 3 over here, so it's the dimension of the underlying space. And so this is the equation. It's a heat equation with a cubic perturbation, and it's driven with an additive space-time white noise. Okay, so another problem So another equation that we're interested in is the parabolic Anderson model. So this is again a heat equation, but now we have a multiplicative. We have some sort of a function f of u, and it's multiplied by a noise psi. And again, it's not for our purposes not so important what the nature of these noises is, but this parabolic Anderson model, we take psi just to be white in space, but not in time. So somehow you don't need to always take space-time white noise. And I haven't actually even defined what space-time white noise is, really so. But again, I will collect its important properties later. And we're also allowed to actually take the underlying dimension d. So I remind you the dimension d is this, on the previous slide, it was this dimension d of the torus. So this will always be the dimension of the underlying space coordinates. We can actually take d to be 0 as well, in which case we just left with the time parameter, so just the r plus. And this is, and in this case, we basically reduce down to the theory of stochastic differential equations, so classical Ito stochastic differential equations, or possibly non-Ito if the noises are not Brownian. So these equations often appear in mathematical physics. So for example, this dynamical 543 model is the stochastic quantization equation for an associated quantum field theory. This parabolic Anderson model represents evolution of populations through a density. So through some sort of a random medium. So the psi is supposed to represent somehow places where the population is either favored or disfavored, and they die or are born with a certain rate that's depending on psi in different locations in space. So this appears in mathematical biology, and then stochastic classical kind of one-dimensional or where the little d is 0 stochastic differential equations appear in also quite a variety of contexts like mathematical finites. Okay, so what we would like in studying these types of equations is that we would like to have some sort of continuous dependence of the solution on the noise. So if I give you a noise, you would like to somehow be able to solve this equation in a way that if I perturb the noise a little bit, then the solution perturbs only a little bit. So we'd like to have some sort of continuous dependence. One of the nice things if we can have such a continuous dependence is that we can, it's very simple then to say what we mean by solution. We would simply say, well, if I approximate my noise psi by some smooth approximations, so typically this psi will not be some sort of a smooth function, but maybe I can take smooth approximations of it via mollifiers. Then if I have this kind of continuous dependence, then I would know that these u epsilons, they also have to converge to something. And the something which is u is what I would call the solution to this PDE. So this is one of the ways of in PDE theory of how you define what a solution is when it's not a classical kind of strong solution, when it's not actually differentiable. You do it via approximation. So, but one of the main difficulties in carrying this out is that all of these equations that I mentioned, they are singular. So what this means is that they contain some sort of products that are not classically well defined in the spaces in which the solution lives. So for example, let's take the 543 equation. One of the important properties of white noise that appears in this equation is that it belongs to a space of distribution. So here, this is called the Holder-Bess of spaces, which are kind of generalization of Holder spaces, but to negative indexes. So these are not functions. So it belongs to a Holder-Bess of space of regularity alpha, where alpha is below -5/2. So don't worry for the moment where these exponents necessarily come from, but I can explain later if anyone is interested. But it turns out that it belongs to this space almost surely, only for alpha smaller than 5/2. Then these Holder spaces are kind of act nicely with the heat equation. So the heat equation, if you invert the heat operator and you apply it to a function in the space, then it essentially gains two derivatives. So you expect the solution u, because you have this kind of nice heat operator here, you expect the solution u to be inside C alpha plus 2, but not any better, because the white noise is not in any better space. And then the fact that this alpha plus 2 is still negative, so this -5/2 is smaller than 2, so if you add 2 to it, it still remains negative. means that you're trying to sort of inside the equation, you're trying to take the cube of a distribution. And this is not a well-defined operation. Generically, there's no way to square or to cube or multiply two arbitrary distributions together. Okay, so this is the problem that one encounters when trying to solve rigorously these equations, or when trying to approximate them. And in fact, actually, I want to illustrate an example where this is even visible on the level of ordinary differential equations. You don't need to look at stochastic partial differential equations. So this result was actually first for ordinary differential equations realized by Line. So he realized that there's no notion of integration that or no notion of solving a stochastic differential equation, which is sort of extends the smooth case. So in a way that kind of it's a genuine extension of smooth solutions, but at the same time encompasses trajectories of Brownian motion. So the precise statement said that there's no notion of a solution in a linear Banach space. I don't necessarily want to state that precise result, but I want to illustrate it in a picture here. So these are two pictures of Brownian motions, psi1 and psi2, or rather derivatives of Brownian motion, so white noises, which are extremely close to each other. So this orange line and the blue line, they are two Brownian motions in both pictures, which are coupled. So they're not independent of each other, so they look almost identical. In fact, to the naked eye, we can't really tell them apart. So this picture here looks almost the same as this picture here. In fact, yeah, I think to the naked eye, we can't tell the difference. But when you use these two, when you use the first kind of pair of Brownian motions as the kind of the psi1 and the psi2 inside this differential equation, so this is like u maybe 1 or something, and this is u2, and this is psi1 and this is psi2. Then you see that actually the solutions are appreciably different. So the solutions become very, very different, even though the noises are quite close. So U1 is actually very different from U2. So this shows that there's not really any kind of stability that one can hope for these kinds of differential equations if one works only in linear spaces. So one needs to kind of keep track of further information about psi1 and psi2 that isn't encoded just by looking somehow at their kind of how close they are as functions. Okay, and I'll again try to explain this in a few slides. Okay, so so let's try to see how to overcome this issue of lack of stability for these equations. So let me focus again on the 543 equation. So let me write simply for the inverse of the heat operator, I'm going to write it as G. And then in integral form, I can rewrite my equation. Like this. There's also some kind of terms that I should include because of the initial condition, which I ignore here. So I'm only focused. This is just a heuristic introduction anyway, so I'll not try to make things rigorous at the moment. But if we do the usual kind of power counting that I was mentioning before, so we expect like psi to be worse than C5/2, then if you convolve with the heat operator, you expect it, with the heat kernel, sorry, you expect it to be of regularity a little bit less than -0.5, so delta here is something very small but positive. So then we kind of, if we could make sense of the U cubed, then we would expect it to kind of triple its regularity or make it 3 times as worse. So we expect that U cubed should be -3/2 minus 3/2. And so then this term here, when you convolve it again with the heat kernel, which is, so that's the term that appears here, you expect it to be of positive regularity. So you expect it to be a little bit worse than a half Holder function. So then what you can do is you can make then the ansatz that, okay, well, I'm going to then just simply rewrite my solution as the linear, as the kind of the solution to the linear equation, plus a remainder, where this remainder is a little bit worse than has hold of regularity a little bit worse than a half. And then when you substitute this back, so if you make this ansatz, then you substitute this back into the equation, you'll see that it reveals a kind of quite a simple form, which is that you still have this linear part, and then you have this. If you expand the nonlinearity, you see that these are the kind of the leading terms that involve g convolved with xi and various powers of it. And then you have this r tilde, which is going to be always well defined, provided that r is 1/2 minus delta, or at least it's not. It should be better behaved than r. Let's put it that way. So not necessarily always well defined, better behaved. And now the idea is that, well, we've made this kind of like better expansion of the solution. So we said, okay, we've made this ansatz that how we expect the solution to look like. And then we've deduced something from there. And then we see that you have these cubic terms and this square term appear. So then the idea is that so these terms are not dependent on the solution. They are kind of just given by the xi. So xi, you should always view xi as the input, and then the solution u is what you tried to find. So this g convolved with xi is part of the input somehow. And the idea is now not to view u only as a function of the input xi, but also of these powers. So g convolved with xi cubed and g convolved with xi squared. And it turns out that this kind of expansion, so doing it just to this one-step iteration, is enough if we were working with 542. So if the spatial dimension was dimension 2, because the noise is much less singular in that case. So the noise is c minus 2 rather than c minus 5 over 2. So it would be a much better, it's a distribution of much better regularity in dimension 2. But actually in dimension 3, one needs to go further and make further expansions. So this is just a disclaimer that what I'm saying is not, so it's actually a little bit more complicated than this in practice. But the idea is the same. So you want to view, okay. So then, however, one of the issues, and now we're getting to the heart of what's going to be the topic and where Preely algebras are going to come in, is the fact that we can't expect this these cubes and the square to actually be well defined in a way. Like if you take, for example, a mollification of your noise, and you look at g convolved with psi epsilon, where epsilon is the scale of mollification, and you look at this thing as cubed, that would be a naive way to try to define the cube of this distribution. This is not going to converge, and this is what this example is showing us. So precisely. So I don't know why I have this divergence here, just to get that. So for psi, so if you mollify the white noise on, then for a generic test function psi, if you take its square, or also the same is true for its cube, and you test so this is now going to give, this is somehow going to be what you would hope to be the approximation of that square. If you test it against a test function, then this is going to diverge in any sense that you want, almost surely, or in any LP space and probability. So you can't kind of naively define this square. However, what is possible to do is that you can define the square after you modify it somehow. And so this modification is what in the theory is often called renormalisation. So in the result that's relevant to our discussion here is that there exist these so-called Wick powers. So you can take you can kind of define a new square. This new square is given by taking a constant c epsilon, which for us is just going to be the expectation of the square of this approximation at some point, like 0. So here I remind you that psi epsilon is psi convolved with some sort of a smooth mollifier. We'll call it chi epsilon. So chi epsilon is a mollified scale epsilon. So this is a smooth. So g convolved with psi epsilon is smooth. It's a smooth random function. So then you can just subtract the deterministic constant from this square, and then actually as epsilon goes to 0, you're going to have convergence, and again in any sort of sense that you like, towards some distribution, random distribution, and this is what you call, so this convergence is how you define this random variable. So this random variable is defined by this convergence. Okay, and then similarly for the cube. So but for the cube you have to subtract 3 c epsilon times, and then you have to multiply it by g convolved with the psi epsilon. So these are these kinds of results largely follow from Wick's theorem for products of Gaussians. Okay, so the punchline here is that one needs to actually modify these naive squares and cubes and other functions in order to have them well behaved. Okay, so then the question is, so if we're able to modify this square, so just to briefly summarize, so the idea was that we wanted to view psi as or to view u as a function of psi plus this cube in the square, and we have to treat this cube in the square as auxiliary input. These are not going to be continuous functions of psi. And then we said, well, to get them to be well defined, we need to change the meaning of the square and the cube for, say, for smooth approximations of the noise. But then if you change this meaning, what does it really mean on the level of the PDE? So what does it mean to solve this original equation, where we have substituted the meaning of the square of g convolved with psi epsilon and g convolved with psi epsilon cubed by these so-called Wick powers. And so I claim, and I'll show you a quick computation to justify this, is that this amounts to solving a classical PDE, but which is exactly like our usual PDE here, except that we've subtracted off 3c epsilon times u epsilon. So we've renormalized the PDE. Okay, so why is this a reasonable claim? So recall that we've made this ansatz that u epsilon is given by this g convolved with psi epsilon plus r. So then if we substitute this back into the equation, we ended up with this expression. So these are the same expressions that we had a couple of slides ago. So there's nothing new at this stage. But now what we want to do is we want to replace, so I said we need to replace these naive squares and the cubes by modified values to have them converge to some sort of a limit. So we're going to replace the square by the square minus this constant c epsilon. We're going to replace the cube by the cube minus 3 c epsilon times g convolved with psi epsilon. So then if we do that, then we pick up the green term here that I've put this in purple. So this term here comes from modifying this expression, the cube, and the red one here comes from modifying this part. So this part and this part go together, because and we had the 3 here because this is coming from the cube part of the that 3 is coming from this 3 here. Okay, now we realize that well, we're left with essentially the same expansion like we had before. So this part is going to be the same as this part here. And I think all of these are supposed to be minuses. Sorry, so those are typos. And here we see there's maybe at this stage it's not such a miracle, but in general it's, a priori you might think there's no reason for this to happen, but somehow this 3 that came from this cube combines with this 3 that came from the other cube. I mean, it's kind of the same cube, but the point is that this 3 came from the renormalisation of this guy over here. So it kind of is related to that cube, but it's a bit different for a different nature. I see there's a question. Are there other renormalization forms that could work, or is your choice the only one that works? So there are other renormalizations that are possible to make this convergence happen. The convergence of the previous proposition, or was it this one here? So you can, if you mean like how much freedom do we have in in this proposition, but basically all the other renormalizations, at least the ones that are kind of like subtracting a constant and not something that depends on space or something like this, is essentially going to be like you can have this exact C epsilon plus something of order one. So it's just like a small shift of your so this C epsilon generically C epsilon diverges as epsilon goes to infinity. So somehow these constants diverge, but you can make them um, you can add to them a finite number, and then you'll still have convergence to a different limit. But this is essentially the only flexibility that you have. I don't know if that answers your question. Okay, okay, I'll continue for the moment. Okay, so now going back to this computation, we see that this three and this three, so the two threes, they actually combine to give you this final three over here. And this factors out as G convolved with U epsilon because of this ansatz that we had here. This R is the same as this R. And so we see in the end that this is the same, precisely the same thing as having the 3 minus C epsilon U epsilon here. So we indeed solve the same renormalized PDE from the previous claim. So yeah, a priori was somehow maybe a small miracle that somehow this 3 really was the same 3 as the 3 in the second line, and so they really combined together to give you a very clean renormalized equation in the end. When this theory was actually being developed, so the framework that made all of this rigorous was actually first introduced by Martin Heyer back in 10 years ago now, it's 2014. And these kinds of computations were done by hand essentially. So kind of to work out what the renormalized PD actually was, one computed these expressions by hand, substituted them back into themselves, and so what the renormalized equation was going to be. And there was no kind of there was an expectation this was general, but there was no proof back at the time. So then it took a few years, and this was the point of the paper or the idea that I'm presenting here, to understand that this was actually a very generic feature. So this was something that always happens. You always get a clean renormalized PDE no matter what equation you're working with. And the way to get to this PDE or to prove that this always happens relied on pre algebras. Okay, so so let me first actually I want to first give the actual theorem that one can state. So this is a generalization of that theorem that of these kind of computation that I did for 5.3. So the theorem is that for any nice equation, and I'm not going to again specify because I'm not going to specify the analytic constraints on this equation, or even really describe the full algebraic constraints in the equation for lack of time. But let me just sort of say that for a wide class, but still quite nice equations, in particular, there's this word subcritical here, which again I can explain afterwards if there are questions, but I'll leave it like this for now. You can always find a finite collection of epsilon-dependent constants, epsilon-dependent functions. So I'm going to denote them as f epsilon tau. So tau here is the index. So for this theorem, tau plays the role of an index set, which is finite. So there's always a finite number of taus. So these are functions of u, and again, the jet of u, such that solutions to the classical PDE, so this is now a smooth PDE. I've mollified my noises. I've replaced each noise by its mollification. if I solve these now classical smooth PDEs and I take epsilon to 0, I remove the multiplication, and I insert this finite number of counter terms, which maybe diverge with as epsilon goes to 0, but that's okay. Then these u epsilons, they actually converge to a limit, converge to a limiting random solution of the. That's what we call the solution of the stochastic PDE for this given choice of renormalized um, with this given choice of renormalization functions. And again, these maybe to Yanis's question as to how much freedom you have in these functions. Again, they are essentially unique, but you can perturb them by small by small quantities to make them. Typically, they will diverge, and they have to diverge at the right rate. But you can shift them by something of order 1. So they're not unique. These functions are not unique, but they exist, which is the important part. Okay, so now in the rest of the talks, I think I'm over halfway. I want to give a brief outline of how we prove this result. And actually, yeah, I haven't actually mentioned any real algebra actually yet in my talk. So now I'm going to try and give a very brief outline as to how Preely algebras in particular enter into this. So this result is somehow, when you see it, it's completely independent of anything algebraic. It's a purely probabilistic or analytic result. It's a result in stochastic analysis. But interestingly, the proof is algebraic. Okay, so this is a very, I want to first present a very schematic point of view because this result relies on not only the paper that and where we employ Preely algebras, but it relies on a couple of other works. So I wanted to present how these works fit together and what the picture that one should keep in mind is. So the very basic idea is that one starts with random approximations of the noise in here, so smooth functions, so C infinity functions, xi epsilon. And what one does is one lifts this xi epsilon to what in the jargon of SPDEs is called a model. And models live inside this curly M space, this space here. So that's the space of models. And you should think of a model as the kind of the underlying function xi, plus all of these nonlinear terms that we needed in order to have a good solution theory for PDE. So this like maybe the square of G convolved with xi, maybe the cube as well, and maybe other functions also. And so this big collection of objects is called the model. So at this stage, this model is completely determined by the underlying xi epsilon. So I give you xi epsilon, and of course, G convolved with xi epsilon squared is determined by this. But the point is that we have to modify the square like we did with the Wick powers. So in general, there's no determination between the first and the second component, for example. Then within this space of models, which is much kind of somehow much richer than just these kinds of smooth approximations of a noise. So from the space of models, there exists a continuous solution map. So here I've written it as the composition of two maps. There's this kind of solution map with an A subscript. This is sometimes called an abstract solution map, because it maps from the space of models to some large space of, again, what in the jargon of SPDEs is called model distributions. And then one finally reconstructs an element from the space into a concrete distribution or function, a C alpha function. And it's this object here in C alpha that we ultimately call the solution of the SPDE. And this diagram is kind of commutative in the sense that there's this classical solution map, such that if you lift your noise to a model, you solve. You don't modify it. You don't modify what the meanings of the squares and the cubes are. You just solve the equation, and then you reconstruct it to get an element in C alpha. Then that's the same as just solving the classical equation in the first place. So this is kind of like a consistency relation. So this is a commutative diagram. Okay, that's not the end of the story. There's this third bullet point here, which is that it turns out that there on the space of models, there exist renormalization maps. So these are maps that map from space of models to itself. And for the kind of the choice of noises that we work with, and this choice was implicit in the nice prefactor for the equations that I was looking at on the previous slide. So for these choice of models that we're working with, it turns out that these renormalized models, what I call here the pi hat. So you apply this this map m epsilon to pi epsilon, you get a renormalized model pi hat. This converges, so the pi hat epsilon converges as epsilon goes to 0 within the space of models. So the original pi epsilon will not converge as epsilon goes to 0, but this pi hat does converge. And this was this was somehow the theory that was worked out by a few people. So all of these papers include Martin Heirer, but also the other one, this analytic one, where they prove convergence, of course, this stochastic paper where they prove convergence as epsilon goes to 0, was also done by Ajay Chandra, who's a co-author in the paper I'm discussing. And the fact that the construction of these suitable renormalization maps M epsilon, these were worked out by Yvain, Martin, and Lorenzo Sambotti. And very briefly, this, as I mentioned, this second paper of Chandra and Heirer is stochastic. Well, this other paper where they construct these renormalization maps, it's also algebraic, but it's Hopf algebraic, so it used it relied heavily on ideas from Hopf algebras. And so the final thing that to finish up this picture, what needed to be done, which is where pre-algebras come in, is to understand how in the level of equations, if you renormalize a model up here with some m, then how should you change the underlying equation? So this is what this EQ means. It's an equation. How should you what's kind of the adjoint action, if you like, of the renormalization maps on equations, such that to keep this, so if you lift the noise, you renormalize, then you do this abstract solution map and reconstruction. How should you modify this equation to keep this whole diagram commutative, so that you match with some sort of a classical solution map here? Yeah, and this was the point of this paper that I'm going to present. Okay, so to set things up, so to describe how one proceeds about this, I'll try to yeah, for lack of time, I can't unfortunately give like a complete definitions here. So I'm going to give only like caricature versions of these spaces, because they also actually they take up quite a lot of space to try to define. So yeah, as a disclaimer, some things I say might be a little bit oversimplified, but I think they'll contain the big picture. So let's just focus on a very simple equation. I'm going to take the heat equation plus my first noise. So there should be like a psi1 here, but my psi1 is just going to be 1, so a constant function. And my second one is where I have a noise, so this psi2. So yeah, I wrote here psi1 is equal to 1. So I'm going to denote by this curly T the linear span of certain set of rooted decorated trees, and I'll explain what I mean by this. So I prefer this recursive construction of trees. So every tree can be written down. So in our setting, it can be written down in the following way. So either if it has no edges, then it can be written as a symbol of this type. So you should think of this case as being essentially just a single vertex, so with no edges, and it contains two decorations. It contains J and it contains a decoration P. And J corresponds to the type of noise that's sitting at this node, and P corresponds to a polynomial that's sitting at this node. The kind of maybe the noise is the more important point here. The polynomial here will just kind of come along for the ride. I won't really try to explain where this polynomial or its polynomial comes from. But I think the noise is very intuitive where it comes from. And then if it doesn't, and if it has edges, then it has this distinguished root that has, again, a decoration J and P. Then it has K edges. And these edges themselves, so here you'll have, again, maybe tau 1, tau 2, tau K. And so all of these tau 1 through to tau K, they contain exactly the same structures that of a rooted decorated tree. So they contain a special root. The special root is always sitting on the bottom, plus a bunch of edges leaving that root, with all with decorations. And these edges that connect the root to each respective tree itself comes with the decoration. This comes with decoration P1, P2, and so on and so forth, pk. And these p's, they're always, they're essentially multi-indexes inside. So these are, you should think of them as coming from derivatives of some sort. So these polynomials, they actually come from Taylor functions. So you have, this is kind of the space of multi-indexes of possible derivatives, and x to the p is the corresponding polynomial for that. So what's natural to do is to every single tree of this type, we associate a function, a space-time function. The space-time function takes on this form. So it's defined, the reason I introduced these trees into this recursive way is that this function is defined most easily through recursion. So what you do is that for a tree of this form, for the tree of like this, if this was tau, then pi of tau at a point x is given by, well, you take the polynomial x to the p, you take the noise xi1 or xi2, so this j always belongs to the index set 1 and 2, so it's either 1 or the noise xi2. And then you take a product of derivatives of the heat kernel convolved with pi evaluated at the previous trees. So this generalizes this these like the squares and the cubes of g convolved with xi that we've seen before. So for example, the square, so g convolved with xi epsilon, say cubed, then this could be represented as pi of this kind of a tree that looks like this. It has three nodes, and where these would be like so there's no all the polynomial decorations would be 0, and the 3 decorations of the noise would be all 2s somehow. So maybe this was the xi2 epsilon. Xi2, all of these would be 2s, but over here we would have a 1 for the noise decoration because we don't multiply anything by the root. We don't multiply it by noise root, we multiply just by xi1. Okay, so this pi kind of systematically encodes all of these polynomials or nonlinear functions of the noise that we obtain if we Taylor expand or kind of substitute the equation back into itself many times. It's the kind of object that appears in the perturbative expansion of the solution. Okay, so I'm going to collect the important properties of from these two papers, the one of Bruned, Hayres, Zambati, and Chandra and Hayre that are already mentioned before. So the first one is that there are maps on these spaces of trees T that map T to T, so that the renormalized model, so pi. So this renormalized model pi hat epsilon is simply given at a tree tau is simply given by applying m epsilon to tau and feeding into it. And there should be of course a little epsilon down here. So and applying it there the canonical by epsilon to it. Okay, so this kind of the statement is that there exist these maps m epsilon that maps models to models somehow. And again, I haven't really given a proper definition of a model, but think of it as the objects that you can feed into an equation so that you get a continuous solution theory. Sufficiently large object that you can feed into an equation. And if you're wondering where these maps come from, they can actually be described quite nicely via a co-action of some other Hauptalgebra on the space of trees. So the space of trees is going to be a co-module with respect to another Hauptalgebra. So they take a quite a tractable form. This other Hauptalgebra is called the extraction contraction Hauptalgebra. And then there's this other result of Chandra and Hara saying that well then actually there always exists a choice for these m epsilons, or more precisely for these so these L epsilons are characters on the other Hauptalgebra. So there's always a choice of these characters such that these resulting pi hats, they converge in the space of models as epsilon goes to 0. Okay, so now we want to understand how this m epsilon affects the equations. So we're going to define nonlinearities. So rather recall that we have these nonlinearities that are functions of the solution and its jet. So really these are smooth functions from r to the n to the d plus 1. So this is like all the possible values of u, its derivatives, its second order derivative, its third order derivatives, and so on and so forth. And it takes values in r, so because I'm just in the real valued case. And I'm going to define, so on this space of all possible nonlinearities, I'm going to define two differential operators. One of them is simply just differentiating with respect to the coordinate p. And the other one is simply, so p is an element of d plus 1. And the other one is something a little bit more complicated. In fact, maybe I won't actually, because this will never appear, so I'm not, let me not comment about this for sake of time. But the important part about this first differential operator is that it satisfies a type of multi-Preely identity. So it's so the space of nonlinearities, C epsilon, C infinity of this big kind of infinite dimensional space, equipped with the following products. So this is a p-dependent product. You take f and g, and you differentiate g with respect to the pth coordinate, and you multiply by f. This forms what one calls a multi-Preely algebra. So in particular, it satisfies this identity. So Preely algebras are non-associative generically. But their associators are invariant under switching so this is a left Preely algebra to be precise. It's invariant under switching the left two components. So here, this is the associator of f, g, and h with the two different products, p and q. Then if you swap, and generically it doesn't vanish, but if you swap the left two components, g and f, you swap them here and you swap them here, then the whole expression remains invariant. And here I've also swapped the q and the p's. Actually, for this equality, it's not so important that I swap the q and the p, because the dp and dq actually commute. But for the analogous expression at the level of trees, this will be important. Okay, and now what we're going to do is so starting off with this f1 and f2 that we had. So remember, f1 and f2 were the two initial nonlinearities inside my equation. Usually there could be many more of them, but let's just stick with two of them. Starting off with with my two initial nonlinearities. For every decorated rooted tree tau inside of the space CT, I'm going to define a new nonlinearity, f of tau, in the following way. So in the base case, if I have, if tau is just a noise psi j multiplied by xp, so there's no edges, somehow the base case, then f of tau is simply just the pth derivative of f of j. Where this derivative was the derivative that I ignored on the previous slide. So maybe think about the case when p is 0, in which case it doesn't appear. So it's just kind of the first nonlinearity that one sees. And then inductively for every other tree, so if we have a tree like we had on some of the previous slides, you take so we have J and P at the bottom, and then we have these K edges. You simply take the F that appears so this is tau 1, tau K. You look at what F was for all the previous trees, tau 1 through to tau K. You stick them in the front. And then you look at the decorations that appear here. And there were also these decorations down here. Okay, so this P again corresponds to this differential operator here, so maybe don't worry so much about that. But then you have these decorations P1 through to Pk, and these are going to be differential operators that act on the function initial nonlinearity Fj, which is the noise decoration at the root. Okay, so there's kind of a very completely inductive definition of these F taus. Sorry. Yeah, that's it. And then you stick some sort of a combinatorial factor in the front, which I'm not going to worry about so much. And then there's a few crucial properties of this construction. I think, don't worry, my time is running out, but I think I'm almost finished. I can maybe get to the punchline of what I want to get to. So there's a few crucial properties of these definitions that I've just mentioned, and proving these was somehow the core of the work. Sorry, I'll just turn the light on. It's getting dark. Apologies. Okay. So it turns out that so where do these F taus really come from? So they actually come from this procedure that we already saw with phi4. You kind of feed the equation back into itself many, many times. In fact, you can always expand the solution as in terms of these nonlinearities plus these polynomials pi that these functions capital pi that we had before. So they kind of appear entirely from kind of the Picard iteration that helps us solve our PDE. So this is in some sense, if you like, where they actually come from, these F taus. And now they come with some actually very important properties. So on the space of trees, there actually exists a bunch of Preely products, again, also indexed by P, just like the previous Preely products were. And these are types of grafting operators, where you graft a tree onto another tree using an edge with decoration P, such that it satisfies Preely morphism identity. So if you graft tau into sigma, and you apply F to it, then it's the same as applying taking the Preely product of F tau and F sigma with this decoration P. So these Preely products on the space of trees kind of come from linearizations of certain Hopf algebra on trees. And what's very important also is that these renormalisation maps, or specifically their adjoints. So if you equip the space of products with suitable in a space of trees with a suitable in a product, and you define an adjoint of the renormalisation maps of this inner product, then you obtain that these renormalisation maps actually form a Preely morphism. And the final property that we need is that this space of trees with these Preely products is generated, or specifically it's freely generated by a bunch of very simple generators. So basically it's generated by the noise by the trees that only have a single vertex. Okay, so these are important properties that one needs to verify. And so with these properties, one can, with these, so far this is just again a definition. So then for one can starting off with a nonlinearity F1, F2, one can define a new nonlinearity F tilde. So F tilde of 2 is equal to just F2, but F1 of tilde is given by applying this adjoint to the single edge, so to the the vertex that just has a single noise declaration 1. Okay, so this is just kind of a definition. But then there's a kind of a very nice lemma, which is that if you take this new nonlinearity f tilde and you feed a tree tau into it, this is the same as taking your previous nonlinearity and evaluating it on m star epsilon of tau. So there's this relationship between the two of them. And this this you obtain by essentially, so I give a proof here, but I think the proof is even too long. You basically, both of these maps as a functions of tau are pre-morphisms. So all you have to do by the previous properties that we've just described. So all you have to do is just check that they agree on the generators. But we know that the generators are very simple objects. They're just single vertices, and this can be done by hand. So this is where the idea of pre-the algebras actually plays a role. So this lemma is somehow the key to understanding what renormalized equations look like. And so maybe just to illustrate that point, so how does one actually in practice get the renormalized equation back? So one rewrites the solution U as this expansion. This was the crucial property 1, where these f taus really came from. And this here we have, because we're working with the renormalized model, you have this pi hat appearing here. So then by the definition, you have this this is pi of m epsilon of tau. But then with the adjoints, you can, so we have f of tau is a linear function of tau. So, and here we have m epsilon of tau, and we're summing over tau. So by kind of the adjoint identity, you can substitute this m epsilon by a tau at the price of substituting this one by m star of tau. And then by the previous lemma, sorry, so this by the lemma should actually go on the next slide. So it's this thing that that you get by the previous lemma. You get that this is equal to this f tilde. So then this f tilde that actually you obtain with this kind of maybe ad hoc looking definition is actually the renormalized nonlinearity that one sees at the end. Okay, there's this kind of a picture as to how this renormalization group acts with the f, but okay, let me not try to explain it right now. So okay, so just to very briefly summarize, there's this kind of very general renormalization theorem for subcritical stochastic PDEs, and the problem is very much probabilistic or analytic, if you like. But the proof is very algebraic, which I think is kind of nice. There's this kind of synthesis of fields in this. And the key structure again was this having some sort of a multi-pre-Lie algebra and morphisms between them and understanding the generators of these pre-Lie algebras that appear. Okay, so with that, I would like to thank you for your attention, and I can take any questions.
Thank you very much for your interesting talk. Are there any questions? There is a question on the chat.
Yes, does your work relate somehow to the work of Cedric Villani? I'm not sure. I guess Cedric Villani has had also actually quite a large body of works. So I'm not particularly sure. Yeah, I would probably say no, being conservative, but maybe on some level there's some relationship with some of his work. And he's worked on stochastic analysis as well. So yeah, sorry, I can't give a better answer.
Okay, other questions? Comments or remarks? Okay, if not, let's thank Ilya again. And,
Thank you.
Okay, we will resume as usual on next Monday at the same time. Okay, maybe we will have the change of time next week. I don't know. I'm not sure about this. Okay, in any case, you will receive the email from Ivan some days before. Okay. Bye-bye. See you.